I chose to do time because last year for my PIP I chose a topic that I didn't have very much fun doing it. So this year I wanted to make sure I chose a topic that I had like a lot of fun with, which I did, and I learned a lot. It was really, really awesome. So this is my content slide I'll be going over. So just take a guess. What were the first clocks? Anything? Ben?
Sun.
Mm-hmm. Anyone else? Bella?
Celestial bodies.
Okay. So the sun, the moon, the stars, and the earth, which are all celestial bodies. We use celestial bodies as our clocks because celestial bodies were a big part of our lives and something that we could easily relate to. So, calendars came a long time before clocks, because before clocks we didn't need that time of day that we need now. We just needed the basic of what day it was. So this is a Mayan calendar, and this is Stonehenge, which is speculated to be a type of calendar because a lot of the rocks line up with celestial holidays. So about 500 to 600 years ago was the first time, 5,000 to 6,000 years ago, was the first time that we actually started needing time of day, which was relatively recently in human history. So we needed it for better organization because as we progress as humans, we want to get more and more organized and learn more and more and just make our society the best that we can possibly make it. So we created clocks. So all clocks have two basic necessities: a repetitive and consistent action that can be used to separate and measure increments of time, such as the ticking on a clock, and a visual marker/markers that can be used to help keep track of and count increments of time, like the numbers on a clock. So, sun clocks were the first types of clocks. They were Egyptian clocks, and we start out with obelisks in about 3500 BCE. So obelisks are giant structures that look a lot like this. This is the obelisk in Pax Square. So we have this giant clock right in the middle of downtown, and we don't even use it. So in 1500 BCE, we created the portable sundial, and portability is a very desirable quality in clocks because it means that you can take time anywhere instead of just having one in the center of the town. So in 300 BCE, we started to create better shapes that were more accurate, like half bowls and bowls. And in 600 BCE, we created the merkhet for telling nighttime time. It looks like this, and it tells time by creating a meridian across the sky, which is basically like a line, and then measuring whenever stars cross over the meridian. So water clocks were the next type of clocks, and water clocks were super special because they were the first clock created that was not dependent on the celestial bodies, because the sun clocks used the sun, but this one could run all by itself. So this was really important. So they were first created by the Egyptians, and then later the Greeks took them on in 325 BCE, and the Greeks called them kleposidras, which literally translates to water thieves. So here are two types of water clocks. This type of water clock works by having a large bowl, this one, and then a smaller bowl inside that bowl. So the large bowl is filled with water, and this small bowl has a hole in the bottom of it, so it sinks down and slowly fills with water. And this one is a bowl of water again, but this has a hole in the bottom to let the water leak out at a hopefully consistent rate, and then this would measure how fast it's leaking. But these are inconsistent because the water pressure can vary, and also in the winter, if your water clock froze and broke, then it would just not be very good. So we moved on to better clocks. So technological progression in the Middle Ages pretty much just stopped. Like, we didn't create very much at all in the Middle Ages because we were working mainly on religion. So we actually reverted back to the sundials, and that became the standard clock until we invented the Virgin Foil escapement, which is a weight-driven clock that goes like, that ticks back and forth. But these were inconsistent because the driving force of how fast you start the clock can change, and so we decided that we still needed to move on. So in 1500 AD, Peter Henliam invents the spring-powered clock. So the spring-powered clock was really special because it was the most portable clock we had ever created. You could take it anywhere, it was really small and very useful. But it was not very accurate at all, but no one really cared because it was just so portable that as long as you get close enough. Then, so in 1656, the pendulum clock was created by Christian Huygens, even though Galileo Galilei drew up the plans for the pendulum clock many, many years before Christian Huygens actually created it. So the pendulum, then we created the W.H. Short clock, which I won't really go into much detail about, and then the quartz clocks. So quartz clocks are, your average watch is a quartz clock because it's the most accurate that we had for a while. We have one more accurate clock, but so the quartz clocks work because quartz, whenever you put them under physical pressure, it creates an electromagnetic field around itself so that it vibrates or oscillates, and then we measure those vibrations to turn it into a clock. And then atomic clocks, which is the most accurate type of clock that we have so far today. And atomic clocks work because atomic atoms have resonances, which means that they vibrate at a consistent rate over space and time. So if we had a cesium atom, which is the kind of atom that they use for the atomic clocks, here and now, today, it would have the exact same resonance as 1 billion light years away, 1 billion years from now. So because of this, we had to change the second that we previously had. Because previously the second was just due to the Earth's cycle around the sun, but now the definition of a second is exactly 9,192,631,770 oscillations or vibrations of the cesium atom. So we completely changed the second. So this is a link talking about how 1 second made it the longest year and how important that could be.
$25 at Olive Garden.
Time to stand still Saturday night for exactly 1 second. CBC explains.
It's an extra long weekend. We had 1 second to the clock, and it's called a leap second. It's happened about 25 times in the last 45 years. I believe this will be the 25th time.
The leap second is meant to synchronize our two ways of keeping time. Atomic clocks, which are incredibly precise, and the rotation of the Earth, which is slowing and can change by the day. A writer for the New York Times points out, all the uncertainty makes it tough to plan ahead. One challenge is that the slowing of the Earth is irregular, influenced as it is by the gravitational pull of the sun and the moon, and by the unpredictable changes in the atmosphere and in the planet's molten core. As a consequence, the scientists charged with measuring the Earth's rotation determine the timing of leap seconds only 6 months in advance. Some scientists want to do away with the leap second and just go with atomic clocks, which over the centuries would mean our timekeeping would get out of sync with the sunrise-sunset cycle. But National Geographic explains, adding a second to our clocks can be a huge pain. No clock can accommodate an extra second. Instead, clocks are traditionally stopped at 23:59:59 for 1 second, but life goes on and gets in the way. Mobile phone networks have blacked out in past years when their timekeeping got out of sync because of failure to observe the leap second. The electric power grid is also vulnerable. Leap seconds can be added at the end of June or the end of December, and sometimes both. Fox Business points out, thanks to 2012 being a leap year, the leap second makes this one of the longest years on record.
It's going to be the second longest year in modern history. We're right behind 1972, a 366-day year with 2 additional leap seconds.
UN scientists debated whether to keep adding leap seconds this spring. They're scheduled to decide on the matter in 2015. For Newsy, I'm Christian Bryant. Multiple sources, the real story.
So that was just talking about how 1 second made it like the longest year in history, just 1 second. And also about how the atomic time doesn't quite line up with Earth time because celestial bodies aren't supposed to be exact timekeepers. They're just supposed to sort of be celestial bodies. So, world time. So noon used to be a very, very different thing. Noon was in your town thought that the sun was right above you in the sky. So as you can imagine, noon for every town was completely different. So each town had their very own noon. And this system worked completely fine until the invention of trains and train travel in the Industrial Revolution. So if you cannot already see where this is going, this is like really, really, really bad. So we decided that we had to synchronize time. So this is a world time map. Our world time has 15 time zones separated by population instead of just straight lines down the globe, because otherwise half the city would be in one time zone while the other half would be in a different time zone. And so we originally synchronized time by telegraph, which wasn't a very accurate system, but we changed it so now we have better systems that are more accurate. So this is Sir Isaac Newton. He's the guy that had the gravity theory with the apples, and he also has the theory that time flows like water at a consistent rate for everyone. This is Albert Einstein. And Albert Einstein had sort of a different theory about how time runs. So Albert Einstein believes that time runs a little bit more like a loaf of bread, which we'll explain later. So, space-time. So Einstein also discovered that every single person has their own personal time, and the speed at which this time runs is completely different for everyone. So, my time is completely different and changing all the time compared to you guys' time. So, in the way that our motion through space affects our motion through time. So, if I was going to go outside and go running, then I would be moving a lot through space. But this would mean that because I can only have the same combined amount of movement through space and movement through time, I would be moving slower through time and thus aging slower. But if I decide to sit down later after I run, then I would not be moving very much through space, so I would be moving a whole bunch through time. So I would be aging faster. Einstein decided that space and time could never again be separate things, so he combined them to create space-time. Okay, so this is where I explain the bread. So now is a very fragile thing. Now for me can be completely different and changes all the time. So the bread theory represents time as a whole. So the way that you slice the bread, it becomes, everything that goes on one slice of bread becomes the slice of your now, which changes for everyone. So if we were going to create our now slice, you can just shout out things that are happening right now in any part of space.
Zoe's talking.
Traffic. Snow. The baby's being born.
And death. Okay, and so this would be our now slice, but this is not going to stay the same. It's going to change because of the way that we're angling our cut. So here are two different galaxies, billions of light years away from each other. In this galaxy lives Bob, and in this galaxy lives Joe. So Bob and Joe are currently on the same now slice, but Joe, his milk just soured, and so Joe goes out to the store to get some new milk. So the store is the opposite direction of where Bob's galaxy is, so Joe's moving away from Bob. But because Joe is now moving, he is changing the angle of the way that he's cutting his loaf of space-time bread, because he is aging slower because he's moving through time, so he's moving through space, so he can't move as much through time. So he's completely changed his now slice. It's now Bob and Joe are no longer on the same now slice, but Joe is on the same now slice as Bob's distant early relative. So if Joe gets the milk, comes back to his house, puts it in the refrigerator, gets his dog and goes for a walk in the direction towards Bob's galaxy, then Joe will again change his now slice because now he's moving in again, but in a different direction. So now he's angling his now slice towards Bob's future, distant future. So that just tells you a little bit how fragile now can be. But if I decide to move right now, then it wouldn't change my now slice in comparison to yours because we're so close together. It would, but it's like so small that we don't notice it like at all. But since they're billions of light years away from each other, it changes the angle so much. Okay. So Earth's movement through space does affect our time because we are constantly moving. But since we're all experiencing it at the same time, it doesn't really affect our life in the long term. So, in 1971, Einstein's theory was tested. It involved a jet airplane and 2 atomic clocks. One atomic clock, they were set at the same time. One atomic clock was left on the ground, and the other was put in the jet airplane and flown around the world. So, when they were compared back on the ground, the one on the ground was a few hundred billionths of a second ahead of the one that was flown around the world. So this would prove that Einstein's theory was right about space-time, how if you're moving through time, then you're not moving as much through space, but if you're moving through space, then you're not moving as much through time. So, everything in time is set in stone and predicted, as the Oracle of Delphi may represent, from the time of the Big Bang. So everything that's happening, me presenting to you, everything that has ever happened and ever will happen has been predicted and set in stone from the time of the Big Bang. It was all going to happen. So, is time a consistent flow? Well, we perceive time as a consistent flow, but really our brain can only get one moment at a time, so it orders those moments together much like a flip book, and then our mind slurs them together so it appears that time is flowing, but really we're just getting a whole bunch of snapshots. Okay, so time travel. Gravity greatly affects time. It pulls on time and slows it down. So here's the apartment building theory. So here we have 2 apartments. This is Bob's apartment and this is Joe's apartment, previously used in the space-time theory. And so Bob lives on the bottom floor of this apartment and Joe lives on the top floor of his apartment. So because Bob is closer to the ground, Bob actually has more gravity than Joe. So Bob is aging slower than Joe. No matter how small, he is actually aging slower than Joe, which is pretty amazing. Then we have the black hole theory. So if I were to create a spaceship that were able to orbit a black hole for even just a little amount of time, I could technically travel through time because, long story short, a black hole is created whenever a star collapses in on itself to create a really condensed ball of mass. So because it's so condensed, it has a whole bunch of really focused gravity right in this one spot. And so if I was to orbit it, my gravity would increase by so much that I could travel through time. Because as I'm orbiting this black hole, what would seem like only hours to me would be hundreds of years back on Earth. So time travel to the past is a little bit more far-fetched. Time travel to the past could be possible by a theory that Einstein had about wormholes. So wormholes are basically tunnels that connect different parts of space and time. So this means that just as easily as your average New Yorker would jump onto the subway to get to work, your average everyday time traveler could jump through a wormhole to get to a different part of space and time entirely. Okay, so one great misconception about time travel is that there are no changes ever. You cannot go back in time and change something about the future. So if I didn't turn in my homework yesterday, or on Friday, and then it's late, but I really needed to get it in because then I'd fail out of Omega, and then, so I have to go back in time and give myself the homework that I didn't do so I can turn it in on time. Well, it's already too late for me because I already didn't turn it in. And if I was able to go back in time and give myself the homework, I would have turned it in on time and never had to go back in time in the first place. So, because everything in time is set in stone. Okay. So the arrow of time is the theory that everything goes towards the future in time. But this is not true for movement, because I can walk forwards and then I can turn around and walk backwards the same the way I came. So, because if I had a glass in my hand and I threw it on the ground, it would shatter into a million pieces. But why can't that glass come right back into my hand unbroken? But the laws of physics agree that this actually could have happened. But all I would need to do is reverse all of the velocities of everything in the whole scenario. But this doesn't happen in our universe because of something called entropy, or S equals K log W, the famous equation devised by Ludwig Boltzmann. So entropy is the theory that everything goes from order to disorder. In our universe, this happens because of the Big Bang. It's everything that we do is carrying out entropy and therefore carrying out the force of the Big Bang. As I'm throwing that glass on the ground and it's shattering into a million pieces, I am carrying out the force of the Big Bang. So, the end of time. The universe is constantly expanding quicker, which, as you can imagine, things are going to start expanding too much and deteriorating. So, in about 100 billion years from now, all of the galaxies will be cosmically out of reach from ours. Of course, we'll be not here anymore, and at this point, there'll be no more stars because their light can no longer reach ours. And then, eventually, black holes will dominate the Earth and life will cease to exist. Will dominate everywhere. And so there'll be basically nothing but particles of dust floating around in space. And the whole universe will look a lot like this. And so at this point, time will be no longer necessary because time is the measure of things changing. So because nothing is changing and it's just dust floating around, then time itself will be completely just a memory and time itself will cease to exist. So this is my thesis slide, and time is single-handedly the most influential part of society and my bibliography. Any questions? Any questions at all? Justin?
Is the same theory with the black hole true if we traveled at the speed of light? Would that augment our relationship to time?
It would alter your relationship to time, but it's a different type of altering because it's not using gravity, it's using just the motion theory where because you're going so incredibly fast, now you're aging slower because your time can't move as fast. So you're moving through time slower even though you're moving through space really fast. So then everything else would be aging so much faster than you than it would appear to be traveling through time. Anyone else?
Yes. I'm really curious about where did you get your research from? Because I think you do such a good job of taking these really complex theories and explaining them in a way that I could understand what you're talking about. So I'm really curious, how did you make sense of all this?
Well, I think that my biggest resource for the complicated stuff was this second one. It was a video, and so I had to watch it like 4 times to understand it. It was like super confusing, but I just tried to relate it to sort of my life, and so I could think of it in a way that I could understand, and that sort of helped me to be able to explain to others.
What is the name of the video?
The Illusion Through Time, it's In the Fabric of the Cosmos is like the series. It's a good TV episode. Ready?
In the 1971 test of the atomic clocks, does it matter the direction of the airplane going around the Earth, whether that clock ends up ahead of the still clock or not? I'm just thinking about Superman trying to save us.
It wouldn't because they're like so close together. And also it circled back around and came back, like because they started in the same spot. because with the two different galaxies, they're staying in completely separate spots, but because they meet back at the same spot, then it would be that the one on the ground is always going to be faster.
Okay, so
No matter which way you go.
it's not so much the direction, it doesn't have to do with the Earth spinning around the sun so much at that
No.
point. The relativity of time of those two clocks is just one is still and one is moving.
Yeah,
Okay.
and technically the other one is moving too. It's just like around the Earth. So
Any other questions? You'll all be having questions tonight.
That was amazing, Zoe.
Yes, thank you,
Yeah.
Well,
Zoe.
thank you, Zoe, for putting that on again for us. We appreciate it.